Okay, folks, we have two examples here that I'm going to walk us through so that we understand the structure function impact of the environment on hemoglobin. The first that we are going to discuss is the impact of acidic conditions on hemoglobin. Where do these conditions occur? Well, what's happening is that your tissues are currently undergoing respiration, right? You're breathing oxygen, you're burning sugar, and you are making carbon dioxide. When this carbon dioxide enters the cell, enters the bloodstream, it's actually first converted into bicarbonate. And so release of these protons acidifies the environment. So you'll expect that the blood near your tissues during respiration is going to be more acidic than the blood that is being oxygenated, for example, in the lungs. Now, what happens with this acidic environment? The information is here on the slide, but I'm going to draw us through this. So here's a big zoom in on hemoglobin, and I'm going to make that central cavity nice and big so that we can see what's going on. Here are the hemes as well. Okay, so we are in an acidic environment. That means the concentration of protons is quite high. And I'm not going to draw a million protons, but you get what I mean. What's happening here is that in the central cavity, we have some histidine residues. And these histidine residues can either be protonated or deprotonated. If you take a look at your amino acid handout, you'll see that histidine's pKa is the closest to physiological pH, 7.4. So if the environment of histidine becomes more acidic, it very easily will grab one of these protons. And so rather than having a lone pair and being neutrally charged, you will now all of a sudden have all of these histidines that are protonated and positively charged. Well, what do we know about a bunch of similar charge close together? Coulomb's law tells us that having all these positively charged histidines close together will cause a strong repulsive interaction. And this repulsion will physically open that central cavity. Now, a large central cavity, folks, is seen in the T state, right? This T state has a large central cavity. Oops. So Coulomb's law, repulsion of like charges, leads to an R to T shift. Since the T state does not bind oxygen well, this means that the hemoglobin lets go of its oxygen and delivers it to the tissues where it is needed. That is case study number 1. Case study number 2 involves a molecule called BPG. Very similar to acidic conditions, BPG inhibits the formation of oxyhemoglobin, so it causes oxygen release in the capillaries, which is a good thing for our tissues. How exactly does it work? Well, before I go in and I draw this scenario for you, I need to show you the structure of BPG. So you'll notice that BPG has a negatively charged carboxylate functional group, as well as negatively charged phosphates. So know that this BPG is very negatively charged. Okay, let's get back to our drawing of hemoglobin. So we already know that in this central cavity are some histidines. From our last drawing, right? But we don't need to focus on those for now, but do keep in mind that those exist there because they can play a role with BPG. But regardless of whether histidine is protonated or deprotonated, what you have is the N-terminus of some of these peptides, as well as lysine. And the R group of lysine is positively charged. So already in the central cavity, regardless of histidine, we know there is some amount of positive charge. BPG is very negatively charged. Very negatively charged. So Coulomb's law will tell us that BPG will have a strong, favorable, attractive interaction with the positively charged central cavity because it is negatively charged. But if we go back to this slide real quick, you'll notice that BPG basically fills up the entire space of the central cavity. It isn't huge, but it's big enough that the size of BPG pushes open the central cavity through steric hindrance. I want to clarify that real quick again. So BPG can bind to the central cavity through Coulomb's law because it is charged and the central cavity has many positive charges. But it's able to cause the R to T shift because since it's large and fills that central cavity, it kind of pushes it open, causing steric hindrance. And again, causing that R to T shift. That's all for myoglobin and hemoglobin, folks. We looked at the various graphs of myoglobin and hemoglobin to try to understand their function a little bit. Then we did a bit of a deep dive into hemoglobin, its structure and function, focusing on the R to T shift with 2 case studies there at the very end. And I will leave you with a cat meme. See you in class.